Well, I started with uh, the density operator or density matrix before the puja break. And after that, as you know, there was a puja break, then I was ill, and so there has been a gap. And so I reckon that I have to uh, repeat much of the things that I taught at that time because it's natural for you to forget. So the basic idea is so far we have only been dealing with what are known as pure states. Pure means pure does not mean the things that are only in the eigenstates. Uh, a linear combination of eigenstates is also a pure state in the sense that I know the state. But there may be situations where I am not sure of the state. It could be one of four possibilities, uh, but I know that it is uh, possibility one with some probability, possibility two with some probability, and things like that. Just imagine a situation where you are releasing a collection of, say, silver atoms in the Stern-Gerlach experiment. You do not know in which orientation they are in, but you know that there are these possibilities, and they are, in the z direction. If you measure, half will be up, half will be down. So probabilities, if you want to talk about, I'm just catching one of the uh, atoms, then you know that it will be up with probability half, down with probability half. So the probability distribution you know, but you do not know in which state each one is in. And that kind of situation arises very often, because it will be rather rare to have a situation where you know the state. And in those cases, the mechanism that we adopt is density matrix mechanism. But before we understand that, we'll start with the pure state and then we'll go to the mixed state. So first we start with pure state. Huh? The, in the sorry, the pure state. Sorry. Pure state means it is actually a psi t. It is actually a linear combination of the eigen or the basis vectors. So suppose un are the basis vectors, orthonormal basis vectors. Then your psi t will be Cn un summed over n. Okay. And Cn will be a function of time. So this is the character of a pure state, and we would say that the rho function, rho is an operator. That operator is constructed by not bracket but ket bra. Psi t and obviously this will be a column vector, this will be a row vector, and the product of a column vector and a row vector will be square matrix, and that square matrix is something we are talking about. And our claim is that one of the postulates of quantum mechanics was the psi, the wave function, contains in it all the information that can be obtained about that particular state, particular particle. And the claim is that this matrix also contains the same information. That means everything that you need to know about the system or the outcomes of experiments that can be obtained using this matrix. That's a claim. So let us start by trying to formulate what would you like to know in this kind of system. For example, if you have an observable, say A, So its corresponding operator will be A operator. Then its matrix element its matrix element, that means A is an operator operating on this, and I want to know its matrix elements. So it is basically I need to bracket it with U, N, and A, U, M. So that is your structure of this. So this is our A, N, M. So this is the matrix element, and the matrix element is obtained this way. Now I want to know what is the expectation value of A. The expectation value of A. That will be a function of time. So let me write T. That's what we want to know. And obviously, this is obtained by bracketing A by the state. So it is basically psi T, A operator, and psi T. This is what the expectation value is. That's something that you know. And if I now substitute, I had probably, yeah. If you now substitute this here and here, then what you get is in place of this one and this one, we will substitute, but this one will be a bra. So we have to convert that into a bra. This will be Cn star T, and then the bra, it will be Un, and that is to be summed over n. Then A, and then this will be, I'll use another index. It will be Cm T Un, and now I can take it back, or I have to also sum over m. So this becomes sum over both of them, n comma m, and it will be Cn star T, Cm T, Cm comes forward, and this, what remains is basically the matrix elements of the A matrix. So it is Un, A, Un, it is that. So you notice that these terms are essentially the elements of the density matrix. Density matrix means this. Right? This is the density matrix. Of the pure state. How? So it is, we were talking about this psi T, psi T, and then we can, if you want, this is the matrix, and if I want to obtain the mth element of the matrix, I will have to say its n m element will be, it will be U m psi T, psi T Un. So this is clear that this is the projection of this on the Um eigenstate, that is the basis state, and this one is the same thing, but it's star. So this is clear that this is C M C M T, and this is star of that, C N star T, and you notice that this is nothing but this. So what appears in the uh, when we calculate the expectation value of any observable, it is basically a summation over the elements of uh, the density matrix times the elements of uh, the A matrix. So this is the utility of this, and you can easily see that uh, if you have the psi as a, this will be a column vector, and the column vector's elements will be C1, C2, C3. So it will be dot 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 Cm, and the row vector will be C1, C2, dot 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 Cn, and the elements will be essentially this. So this is the row as an operator. So what are the utility? One utility we have seen, that we can easily find the expectation value of any operator, expectation value of any observable, so long as we know the operator representation of that observable. The next thing is, what is the trace? The trace of rho. This will be the sum over, it will be rho, but the diagonal terms of n sum over n will be function of time, so let me write function of time. This is equal to, it is sum over n. It is essentially the Cn star Cn. So it is mod Cn square. And obviously, since the Cn's come from this representation, the completeness will demand that this is equal to 1. So the matrix will be such, its constraint will be such that the trace will always be equal to 1. Okay. Now let's get back to this. We were calculating the expectation value of an operator A, and we have found that this is equal to the nm summed over nm. It is Cn star T Cm T and A N M. This is what we have found. Now let us work out this. We have already learned that this is the elements, nmth element of the row matrix. So this is sum over n comma m, and the way we obtain the matrix elements, we will exactly apply that. It will be um, the row matrix un, and here it is a nth. So it is, sorry, un, a operator um. It is immediately clear that this is this can be, when you sum over n, this is nothing but 1. So it is basically sum over n, sum over m, row first, then A, then, and this is nothing but the trace of the matrix rho T and A. So if you want to calculate the expectation value of any observable, all we need to do is to obtain that matrix, multiply that with the density matrix, and take the trace. Simple. So these things become rather simple even if we are not working with a mixed state. Even if you are working with a pure state, calculations become very simple using the density matrix. So all that you need to construct is the density matrix, and then everything becomes simple. How does the density matrix evolve with time? It will be d dt of the density matrix. Now this is actually d dt of psi, and therefore there are two terms. I have to do it in two steps. First, I will differentiate this. It is d dt of psi and all the psi's are psi of t. Just I'm not writing because then it will be writing long things. So always remember the psi is a function of t. And then it will be the bra psi plus, first I'll write the ket, which will remain, and then the d dt of the bra. Now, this is something that we know from the Schrodinger equation. It is 1 by IH cross, 1 by IH cross, and the Hamiltonian operating on psi. This time I'm writing the t's because we need to keep in mind that the Hamiltonian can be a function of time. And this one will be, since it is a bra, then d dt of the bra is, then you have to take the conjugate of it, is 1 by minus IH cross. Then it will be first this bra, this ket, and it will be the Hamiltonian operating on this one. But this one is a bra, so first I'll have to write the bra, and then the Hamiltonian will operate on the right side. The writing is important. And it is immediately clear that this will be 1 by IH cross. This is Hamiltonian.
Sir?
Yeah, I have missed something.
Sir, yes, the bra is missing in the second step.
Bra is missing here, right? Yes. That's what is missing, right? Yeah. So this one I have written, but this bra I've missed, so just keep it here. Then this one is nothing but the rho. So H rho, this is rho H. So it is minus. So it is immediately clear this is nothing but H, comma, rho T. Okay. So this is how the density matrix evolves. And the evolution law is reasonably simple, so it is not difficult to remember. So we have found that if we consider a pure state, that then the trace of the density matrix will be 1. We have found that if I want to find the expectation value of any observable, then all I need to do is to take the trace of the density matrix times that particular operator. And third, we have learned that the way, so I can always take this one up there. So it is IH cross DDT of rho T, and then erase this. Then it looks like the Schrodinger equation. And that will be how the matrix evolves. Now, what else can we be interested in knowing? We may be interested in knowing that if I now make an observation, since it was a linear combination of various eigenstates, there are various probabilities of finding each eigenvalue. So I might be interested in knowing what is the probability of finding the eigenvalue, say an. So we might be interested in knowing the probability of finding the eigenvalue so it is P of an. We know that this is nothing but the projection of psi on an. So it is an eigenvector psi, its mod square. And the mod square is nothing but psi star psi. So an psi. Okay. Now, what is this? This is nothing but the projection operator. We know that. Huh? This is the projection operator. Onto the state an. An is the basis state. So this is a projection operator onto the basis state. So projection for the nth basis. So if I know the projection operator for the basis state, then it becomes psi. It is the projection operator of the nth state. So I can write it that way. So this is the projection operator. And we know that this is nothing but the expectation value of the projection operator. See this structure? The projection operator is sandwiched between the psi's, and this is nothing but the expectation value of psi. And we already know that the expectation value of any operator, is nothing but the trace of the density matrix times that operator. So we'll simply apply that. So it becomes trace of the density matrix, the projection operator times the density matrix. It will be a function of time, it will be a function of time. So the probability of finding something is also easily calculable by this. So it becomes very, all the calculations actually become very simple. All you need to do is to do matrix multiplications and obtain the trace of it. By MATLAB, it is just a one-line code. Is the density matrix a Hermitian matrix? In order to check that, we have to look at the adjoint of that. This is the adjoint matrix. Its matrix element will be rho star. It will be nm, and that is, we know that it will be Cm T, Cn star T, and we can see that this is nothing but the same as the matrix element of the rho operator. So the adjoint and that are the same, and so it is Hermitian. So it is Hermitian. All right. So we have calculated whatever we have checked the properties of the uh, the density matrix of a pure state. Now let us take the next step to consider a mixed state. A mixed state's character is that either it can come from an ensemble of possibilities. That means, say, a collection of particles are going, and each might be in different states, and you more or less know the distribution of the states. Suppose it can have four possible states, and 30% of them can be in state 1, 20% of them can be in state 2, and so on and so forth. This gives a probability of finding a particular pure state, and probability is a classical probability. So you have a total collection in which I do not know the state of each one, and that's what we are trying to figure out. I do not know, but we know the proportion of different states, and therefore that is a concept of classical probability, while the probability that we have so far encountered in quantum mechanics is a quantum probability. That's a fundamental probability. That's irreducible probability. So in this case, we are actually encountering two types of probabilities. But that would not be a very big problem, because the first kind of probability, the classical probability, is something that we are very much accustomed with. Okay, let me delete this and let me continue. Okay, now let us continue, and now we'll be considering mixed states. What will happen for the mixed states? Then we have the classical probabilities. Classical probabilities, that will be, say, P1 of finding it in the first pure state, P2 the probability of finding in the second pure state, dot dot dot, it will be some Pi. And then obviously that it will be obvious from your idea of probabilities that sum over Pi should be equal to 1, because it is sure to be found in either of the states. There's a classical probability. Now, in this case, suppose the particle is in one of the states, say pk, so the kth state, the probability when it is in the kth state of finding it with a eigenvalue an will be, so this is a symbol of the probability when it is in the kth state of finding an eigenvalue an will be I have to do the usual procedure. I have to bracket it in k and psi k. It will be the projection operator on the psi k. Okay. So this is something that we have seen. I've just erased it. So this is what the value of the probability of finding in a particular eigenvalue was. We've just deleted it, but if you look at your note, you will find that. So this is the probability. Now, for the kth state, this is the trace of the row of the kth state This is not the mixed state, this is the row the k state times the projection operator of the nth eigenstate. So this will be effectively this. This is something that we have seen from the last page. So we have now we are considering a mixed state where had it been in the kth state, then this is the probability of finding it in the an eigenvalue. But now if I consider the probability in the mixed state of finding the an eigenvalue, then I have to take a sum over all possibilities. So it will be sum over all k's. It will be the probability of being in that kth state times the pk of an, this, and then this will become, it will be sum over k, pk will remain, and this we know that it is the trace of rho in the kth state and the p and the projection operator. Okay. So effectively we are obtaining the, had it been in the kth state, what is the probability of finding the nth eigenvalue, and then sum it over all the possible states. Now I can move the or I can bring the trace up front. The trace of it will be the pk sum over k, pk, and then it will be the rho k. This pk is the probability, and this is the projection. This is the small p, this is the capital P. This, and it is p n. Now this is nothing but the trace of which here it is, this whole thing we will define as the row matrix of the mixed state times Pn. So now I have defined the density matrix of the mixed state is equal to, it is this. It is basically the density matrix of the kth state weighted by the probability of finding that particular state summed over k. So this is important. You have to remember this. This is how we define the density matrix of the mixed state. Again, let me repeat. We write the density matrix of the kth state, the probability of finding the kth state, and sum over k. So that's how we obtain the total density matrix. So this is equal to, again, sum over k, and we know what the density matrix of k is. It is pk, and this one is psi k psi k. So this is the definition of the density matrix of the mixed state. Okay. Now, if I have this as the density matrix, then what information can I extract out of it? Firstly, since pk are real and this row is Hermitian, therefore the whole this density matrix is also Hermitian. So this is Hermitian. Follows from logic. And we had obtained that the trace of uh, of the pure state was 1. Let's check the state of the mixed state density matrix, the trace of that. This will be the K. It will be Pk. Now, here we have to take the trace of the rho K. Now, this is this we knew to be this we knew to be equal to 1, and then the probabilities of different states summed over k is also 1. So this part is also 1. So is equal to 1, which means that the trace of the total, the mixed state density matrix also has the same property, that the trace should be equal to 1. It is a easy way of checking whether, when you write the density matrix, it's an easy way of checking whether you have write it correctly or not. You just sum up the diagonal terms. If they sum to 1, you know that you are at least satisfying one important property of the density matrix. We would be interested in knowing the average value of a observable. Now, this average value will be summed over some n. It will be an, the value that you observe, and the probability of finding that particular value, right? So this is equal to sum of over n, an, times this probability of finding that is something that we have already found. It is the trace of the density matrix times the projection operator on the nth basis. And then we bring the trace out. The trace, it will be the rho, and it will be a sum over an and pn. And we have already seen that this is nothing but the A operator. So this is nothing but trace of rho times the A operator. We have already seen that. In the things that I just erased, you just look at your class note, you will find that this is something that we obtained earlier. So in this case also that property carries. If I want to find out the expectation value of any observable, all I need to do is to obtain the matrix of that observable and multiply by the density matrix take that is. So it is actually pretty simple. What else would you be interested in knowing? We'll be interested in time evolution of the density matrix. So we'll be interested in knowing the time evolution density operator. This state has a probability pk of being in the state psi k. So assume that at times t0, the state has a probability of probability was pk of being found in the state psi k. So that is there's the starting condition, and then we are trying to figure out how it will evolve. Obviously, that distribution of the probabilities will remain the same. So if it has some probability 30.3 of being found in psi 1, that fraction will remain the same as the state evolves by the Schrodinger equation. So that is something that we'll use. So the Schrodinger equation is IH cross ddt of psi t, that is the Hamiltonian operator operating on psi t. And for in the pure state, it will then follow the equation in pure state. IH cross ddt of psi k, the kth state, will follow this equation. So the kth state will evolve according to the same equation. And the mixed state is a collection of these pure states distributed according to some probabilities, and those probabilities remain the same. And they obviously, for the pure state, for the mixed state, due to the property of linearity, it will remain the same. It is basically IH cross ddt of rho t. It will be equal to IH cross ddt of, I'll have to write the expression for rho. It is pk, and it will be rho k t. And so it will be the first one times IH cross ddt of the first one, and so on and so forth. And because of the linearity, each one evolves as the commutator of the Hamiltonian and the matrix. So it will, because of linearity, this will be same as the H t comma rho. Notice, because of the linearity, that argument, this is a summation of IH cross ddt of the probability times the first pure state density matrix plus IH cross ddt of the probability times the second pure state density matrix, and so on and so forth. And for each one, it will satisfy this, and therefore, by linearity for all of them, it will satisfy this equation. So the same equation actually applies for the mixed state also. Another property is that, okay, for the, we'll come to that later. What is the diagonal elements? N. It will be the k, pk, it will be Cn in the kth state. Let me write it this way, mod square. So this essentially says that, let me write it, if the state of the system state of the system is psi k, then the probability of finding it in the eigenstate un, this is this. So the diagonal elements effectively mean this particular thing. That is the diagonal elements. What are the off-diagonal elements? The off-diagonal elements essentially mean off-diagonal elements now notice one thing. This term is always a positive real number times a probability which is a positive real number. And therefore, the matrix, the diagonal elements are all positive real numbers. And each one will add up. So as you add more of the case, it will add up, it will increase. But for the off-diagonal elements, there would be terms like Cn star Cm. So it will be off-diagonal like Cm star Cn. Now that each of these will be complex numbers, and if you multiply that, it doesn't become real. So the whole thing will be complex numbers. So as you add over mn, it will basically, it may cancel off. So the off-diagonal elements can be zero. And what will it represent? It will essentially represent the fact that sometimes you will have interference between the different terms. So it is. So let me write it. I have a little time. Yes, let me write it. For the non-diagonal elements, rho nm, it will be sum over k, the probability of finding it in k. Then it is Cn k Cm star k in the k. Now these elements express the interference effects between the nth and the mth eigenstates. So because of this, this can interfere with each other, this can add to each other, this can subtract from each other. Ultimately, it can also lead to zero value. So all these are possibilities, but the diagonal elements do not have that possibility. Okay. So let me write so that you can also write in your note. These express the interference effects between states un and which this will appear which appears when you have got a psi k, the state is a linear superposition. So if the state is a linear superposition of the eigenstates, then there can be such interference effects between these states. The rho nm is the average of these cross terms. It's the average of these cross terms over all states, because it is summed over k. on states in the statistical mixture. And since these can be complex numbers, the complex numbers can add or subtract from each other, like the usual interference. These can also be zero. Can be zero. It will not be that it will be zero. So this is just a summation of all possibilities. So this can be zero, but the diagonal terms cannot be. Now you can see that if we have a mixture of states, and if we are able to write down this the matrix row, then that contains all the information necessary. If I know that, I can tell that if I now perform an experiment, what is the probability that I'll see a particle with a eigenvalue, say an. I can easily say that. If I keep on observing a large number of such particles, what is the expectation value of that particular observable? We can find that. And so whatever we want to know about the system, which is in a mixed state, that information is contained in this matrix. And therefore, that matrix is a very powerful tool in many of the future courses that we'll take. Many future courses will almost do the whole quantum mechanics in terms of the density matrix.
I had a question regarding the time evolution of these density matrices.
Yes.
So, when we consider how density matrix evolves, are we considering pk to be independent of time, where pk is that probability that it is in some particular pure state?
Yes, that's because when it starts, it has some distribution of those probabilities. Okay. And as it evolves by the unitary evolution given by the Schrodinger equation, those probabilities do not change. So if it had been in a state k with, say, probability 30%, as the state k evolves, the probability 30% remains. Okay. So the probabilities do not evolve. What evolves are the states. And as a result of that, we have that simple expression that the density matrix, its evolution is also given by the commutator of the density matrix and the Hamiltonian.
Okay.
Any other question? If not, let's stop.